Now let's talk about the potentials. There will be so many potentials in the body, like the resting membrane potential, equilibrium potential, then graded potential and action potential. So first, coming to the resting membrane potential. As the term suggests, it is at the rest. So whichever ionic movement is happening and finally they contribute to some potential at rest, it is called as resting membrane potential. And resting membrane potential is contributed by all the ion channels which are open at rest. For example, a cell membrane is there and there are different ion channels like sodium, potassium, chloride, all of them. Whatever ion channels are present and whatever potential they are contributing at rest, then it becomes the resting membrane potential. Then what is equilibrium potential? The potential which is contributed by a single ion, only one ion. If I talk about a single ion, like for example in this case, if I talk about the potential of only potassium, then it becomes the equilibrium potential. Equilibrium potential is for a single ion, resting membrane potential is by all the ions. So the scientists, what they did first, they wanted to study the resting membrane potential. So they took one specific cell. That cell is nothing but the glial cell. And there is a specific reason for choosing this cell. This cell was permeable to only one ion, that is the potassium ion. So it becomes easy for them to study the resting membrane potential because only one ion channel is present and only one transport of a substance is present. So what they did is they tried to understand the RMP through this glial cell and applied the same phenomena to all other cells. When they studied, what happened was at rest, this is the resting membrane potential concept. At rest, what was happening is inside the cell sodium is more or potassium is more. Inside the cell potassium is more. Because already we saw in the general physiology itself, sodium chloride is like a C, it is on the outside, it is more, whereas potassium is more on the inside. So first, from the inside, the potassium channels are open. Some of the potassium channels are open. So what will happen? Due to the chemical gradient, it will move from one place to the another. Where does it move? From the inside of the cell, it moves to the outside. Inside to outside. Why is this happening? Because inside the quantity is more. This is because of the chemical gradient. This gradient is also called as chemical gradient because the chemicals are more here. But this happens until some point only. Why? Because as and when the potassium starts to move, the outside positivity starts to increase. The outside positivity starts to increase. Now what happens is outside it is more positive. So the same channels, some of them, what they will do is they will transport the potassium back into the cell. Why is this happening? This is because the electrical gradient. So the second thing that is happening is electrical gradient. So chemical gradient is throwing out, electrical gradient is bringing in. But at some point of time, this movement goes to and fro, to and fro, to and fro. And finally, they will come for an equilibrium. At equilibrium, some of them will be flowing in, some of them will be flowing out. But finally, they will be at a static state, that is the equilibrium state. This third state, that is the equilibrium state, electrochemical, we can say, because both are there, electrochemical equilibrium. Finally, some of them are going out, some of them are coming inside. So this becomes an electrochemical equilibrium and creates one potential that is called as equilibrium potential. This is the equilibrium potential for a single ion. I told you if it is for a single ion, then we'll call it equilibrium potential for potassium. The same thing happens for rest of the ion channels also. Whichever is open at rest, they will be having a chemical gradient and they will be having an electrical gradient also. So this will mismatch and finally they form an electrochemical equilibrium and they will create a potential that is called as a resting membrane potential. But for a glial cell, what is the resting membrane potential? For a glial cell, there is only one channel open, that is potassium. So the equilibrium potential of potassium becomes the resting membrane potential of the glial cell. And this value is around minus 90 millivolt. This minus 90 is the resting membrane potential for the glial cell and it is the equilibrium potential for the potassium also. But if I calculate it for all the ion channel, then it becomes a resting membrane potential of a normal cell. Then these equations are given by certain formulas. For example, the RMP's equation for a single ion is given by a Nernst equation. We don't want to study the intricate details of Nernst equation. Just remember, for a single ion, it is Nernst equation. For all the ions, if we take into consideration of all the ions, then it is called as Goldman-Katz equation. So this is called as Goldman-Katz equation. Then coming to the RMP, RMP will be contributed by most of the channels, but among them, which is the most important channel, please don't write sodium or sodium potassium ATPase channel. It is only the potassium channel which is maximally open at rest. Why potassium is contributing maximal to the RMP? Because potassium channels are the one which is maximally permeable at rest, maximally open at rest. So that is the reason, because we are studying the rest conditions. We are not giving any stimulus at all. Whenever we give a stimulus, then it is called action potential or gradient potential. We are not giving any stimulus. At rest, this channel is maximally open. So that is the reason why this potassium is contributing maximally to the RMP. Then after that, followed by chloride, then very, very little by the sodium channel. Then all of us go for an option of sodium potassium ATPase. Why we are constantly writing sodium potassium ATPase? Sodium potassium ATPase channel contributes very, very little to the RMP, but the RMP is maintained by, if the question is maintained by, sodium potassium ATPase channel is the answer. If the question is it, because it is the one which is bringing back this resting membrane potential to a maintenance. For example, once the movement of potassium has gone out more, or sodium has gone in more because of their chemical gradient, somebody has to put them back to their original places, and that somebody is done by the beautiful channel, that is the sodium potassium ATPase channel. So sodium potassium ATPase channel does not generate the RMP, it is the maintenance of RMP. It contributes to RMP very, very little. They say it is around minus 4 millivolt to minus 10 millivolt. Very, very little, very, very little. Whereas the RMP is around minus 90, minus 70, around the range. RMP for a glial cell is minus 90, but for a neuronal cell, for a neuron, it is minus 70 millivolts. For a neuron, it is minus 70 millivolts. So we have to remember this information also. So this is all about our resting and the equilibrium potential.